All right, everybody, welcome back. So we're going to start the second session with a presentation from the Web3 Foundation and their very generous platinum tier sponsors of Crypto Economic Systems 2020. So we thank them very much for their support. And also for our other sponsors, Calibra and Cooley Law at the silver level. So we're very grateful to them. We're also presenting this conference in cooperation with Usenix, the Systems Association. We're extremely happy to be partnering with them. And we'd also like to give a big shout out to the MIT Digital Currency Initiative and the MIT Press, who initiated the Crypto Economic Systems project in the first place. So without further ado, I'll introduce Bill Laboon, and he's going to talk about the Polkadot hybrid consensus model that is employed by the Web3 Foundation in the Polkadot implementations. And Bill is the technical education lead for the Web3 Foundation in Zug, where he helps people understand blockchain technology. He's also a lecturer, currently on leave of absence at the Computer Science Department of the University of Pittsburgh after 15 years in the software industry. He frequently speaks at conferences on a variety of topics, including blockchain technology, improving software quality, and ethics of software development. He's the author of 2 books, A Friendly Introduction to Software Testing, an undergraduate textbook, and Strength in Numbers, a near-future novel set in a world in which cryptocurrencies entirely eliminated traditional money. I suppose that is still a bit of a sci-fi notion at the moment, but let's see if we can bring it closer to reality. Thanks, Bill.
All right, thank you. And based on that talk, maybe it wasn't sci-fi enough compared to hyperbarter that we had discussed earlier. So thank you, everyone, for showing up. As Wasim mentioned, I'm here from Switzerland, so it's a bit of a trip for me, but I'm really glad to be here. So first, as I am here from the Web3 Foundation, I figure I should say what the Web3 Foundation is before we jump into the talk. So we are a Switzerland-based foundation in Zug, Switzerland, also known as Crypto Valley. And we are a nonprofit foundation, a Stiftung, in the words, in the German, we're dedicated to nurturing cryptographic technologies that are going to help decentralize the web, preserve privacy, and keep power in the hands of the users. The one particular project that we have been very focused on lately is Polkadot. And so before I talk about our hybrid consensus model, I want to explain from a very high level what Polkadot is, how it differs from other blockchain technologies out there, and then specifically why our choice of consensus model is so important for what we are trying to do with Polkadot. So Polkadot, from a conceptual level, looks kind of like this. We have a central relay chain, which is a very simple blockchain. It doesn't have any smart contract capabilities or anything. Really what it does is just order and organize these parachains that do the actual work. So when you think about using, for instance, a smart contract or a value transfer or anything like that, then you should really be thinking of one of these shards, or as we call them, parachains. So these shards differ from some of the shards you may see in something like Ethereum 2.0 because our parachains are heterogeneous. That is, different parachains can have different capabilities. So you may have a smart contract chain, you may have a privacy-preserving chain, you may have a chain that's optimized for gaming, etc. But all of these can actually communicate with each other as well as share the security of the entire network. So this differs from other inter-blockchain communication systems like Cosmos in that all of these different parachains, all of these different shards are actually sharing the same security model. They're not as independent. The relay chain holds basically the state of the parachains. Again, it does some other things, but again, it's relatively simple. Secured via nominated proof of stake, which is a proof of stake system where it's similar to delegated proof of stake, except that you as a nominator, someone who is sending your stake to a validator, your stake can also be slashed. And so people have to be wary of who they validate. So the validators, we have a number of machines that are in charge of producing blocks. These are the top N stake getters. So there is a limited number of systems that can produce blocks. So a finite number. This number is modifiable. And what we see right now, we actually can have, since we have on-chain governance, it's actually very similar to Tezos. We can have users decide and vote on what the ideal number of validators should be. In our Canary network, which is our initial unaudited version of Polkadot that has been running since August of 19, we have right now 180 validators. However, this number can be moved up and down. These validators are going to be the nodes that actually produce and finalize blocks. They do have some other responsibilities, such as communicating with these parachains that I'm not really going to touch upon. But just know, for the purposes of this talk, these validators, this finite number of validators, are going to be the ones actually creating blocks. They're the ones we're talking about. All right, so again, from a very high level, what we want is a system that can have many different heterogeneous shards, different parachains in our parlance, that can run semi-independently, yet share information with other parachains on the network, as well as share security. We also want to be able to communicate with other blockchains out there. We don't want to have us just be a larger silo. The goal of having Polkadot is to remove silos, and if we're just making it a bigger silo, well, that's good, right? It's a step in the right direction, but we really want to be revolutionary as opposed to evolutionary. So one of the things that we want to do is be able to send data and receive data from these other blockchains. Right now, we're working on what we call bridges. So these bridges to Ethereum, Zcash, and Bitcoin. So all of these are still under work, but they will, once we have them working, be basically virtual parachains. So you'll be able to interact with these systems just as if they were another parachain. So that's the basic idea of what Polkadot is. And it turns out that some of the traditional consensus models, consensus mechanisms that were used are not very well suited to this system. So we came up with this concept of hybrid consensus. So we do want to have finality. So we want to have provable finality in our systems. And as you probably know, using a classic system like blockchain system like Bitcoin, you've got probabilistic finality. That there is no way to prove that there is not some longer chain out there with more work, but rather we can use proof of work, and then it becomes astronomically unlikely that there is some other some other chain out there that has more proof of work on it. There are mechanisms already out there that have provable finality, for example, tendermint, but it turns out these have a very big drawback. They're vulnerable to stalling. If you don't have a large enough number, or percentage rather, of the validators or validator equivalents on these systems, then your system can't be live. You can't progress without some sort of hard fork or some manual intervention once you get below 2/3 of the validators online. So we could work with this sort of system, but we've also found that because we have this interaction with other blockchains, we want to be able to have this non-siloed interaction with these other blockchains, we may occasionally need to revert blocks. So for instance, if some other blockchain there's a man-in-the-middle attack and we get an invalid block, we don't want to have that, oh, well, that's already finalized. You can't go back on it. So we do need to occasionally revert blocks that have been recently added. So ideally, what we wanted was a system where block production would always occur, we could revert, but eventually we could have provable finality, that we could prove to others that were not part of the system that this is the canonical chain, right? Even if you're not involved in it, even if you're not running a full node, and make it much easier to interact with all of these other blockchains out there. Again, because they would not be directly a party to us, we would not directly be a party to them, but if we have provable finality, then we can prove that, all right, this is the right chain that you should be, canonical chain you should be reading from. So what we came up with, and when I say we, I feel like I don't really deserve to be part of the people. Some really smart people came up, some of our researchers, with this concept of hybrid consensus. So this gives us the best of both worlds. Block production is always going to continue as long as at least one validator is online. It will always be live. So blocks will always be produced. So we have one system for that, for block production. However, finalization, similar to like Casper, is done via a separate finalization gadget. So there is, if we think about blocks being produced, we have block 1, block 2, block 3, block 4. I like to think of as sort of someone, a checker or a watchman, following behind a few blocks, looking to say, okay, this one's good, this one's good. So as we're producing blocks 3, 4, 5. That checker is back at 0, 1, 2, a few blocks behind, and finalizing our blocks. In ideal circumstances, this differentiation, this delta of time between when a block is produced and when it's finalized, it's actually rather fast. So generally, a few blocks is what we see empirically, which since we have a 6-second block time in our Canary network, we're seeing about 20 to 30 seconds to finalization. Again, these are in ideal circumstances, though. If there are some issues, we can delay finalization while other checks are done. So for instance, if we get conflicting information about what the current state of a parachain is, we have multiple nodes communicating with us, and one says that situation A happened, another said situation B happened, it may take a while before we can finalize on what the correct version of that is. So we actually can continue producing blocks. Others can work and produce blocks and do transactions and all of that stuff, but we hold off on finalization until all our ducks are in a row, basically, that all of the parachains have given us valid data. In the event of really severe network partitioning or some other sort of Byzantine failure, like a malicious attack, then block production can continue indefinitely, even if a large chunk of validators fall off or are being malicious. And actually, when we talk about Grandpa, we'll see how this is the case. Once we do figure out a canonical chain, once this network partition has been healed, once enough validators get kicked off, we actually can very rapidly bring finalization up to speed. So we don't have to wait for block by block finalization. We can zoom ahead and finalize a huge number of blocks at once. We've actually seen this for real in our network with tens of thousands of blocks, and it can take, in under a minute, we'd be caught back up again with finalization. However, theoretically, we should be able to do millions of blocks. So why do we do this? Obviously hybrid consensus, and as we go through this, you'll see it's a little bit complicated. Has a lot of wrinkles to it in creating a canonical chain and coming up with the best chain rule. But this does allow us to always remain live, always allows parachains that may not be affected. If parachain A is causing problems, this shouldn't hurt parachains B and C from interacting with each other. By having our messaging system be able to continue running, since this is bounded by block production time, not finalization time, it allows us to have fast message passing and reliable message passing. It also allows liveness, even as long as one validator is producing blocks. And this will give us probabilistic finality, but at least we have some sort of quote unquote finality. So the two mechanisms that we do use for this are Babe and Grandpa. So Babe, I like to think of, Babe is the baby. It's crawling ahead. And Grandpa is the one chasing behind it, finalizing things. So Babe is blind assignment for blockchain extension. This is similar to Ouroboros Praus. Validators are going to randomly select themselves to decide when to produce a block. They're selected by the amount of stake. And again, this is just for block production. There is a simple best chain rule that we'll see that can be overridden by Grandpa. So grandpa, ghost-based recursive ancestor deriving prefix agreement, you could tell we love our acronyms at Web3, right? Is going to finalize blocks separately. Again, a block must be produced by Babe first. The baby needs to be crawling ahead, but can finalize for these older blocks. So again, a few steps back from the head. So just as a quick graphic of what this looks like, we'll have a chain between Genesis and some point that we have finalized with grandpa. But after that, there may be some forks, and we'll have to come up with a chain rule to figure these out before grandpa finalizes them. So let's talk about Babe and block production. So Babe is a proof-of-stake protocol. One of the interesting things that differentiates it from others, it doesn't have this. It does have this concept of time, but does not actually use a centralized clock. All of the nodes together actually come up with a time together. In order to understand Babe, we need to understand these concepts of slots and epochs. So a slot is just a n-second period of time where a block may or may not be produced. So we're going to separate time into these discrete quanta of slots. Some number of slots constitute an epoch. And what we're going to do is use those epochs to get randomness in chunks for coming epochs. So, got a beautiful animation here. Right, so we get randomness, and at each slot, all the validators are going to run a verifiable random function. So a function that is going to, using the randomness from previous epochs, determine whether or not they're going to produce a block. This is similar to like a standard, like Bitcoin hashing until proof of work, hashing until you get below a certain value. Except we're just going to throw the dice one time. We're going to see, hey, I'm going to randomly roll a die. Did I get less than a certain value? If so, I can produce a block. Otherwise, I won't. Because this is the case, you'll notice that sometimes multiple validators are going to produce a block with Babe. We saw that. You could have a fork, right? You could have validator 1 and validator 3, for instance, produce a block, and then you're going to have to decide which one to follow. You also notice that sometimes we don't have any blocks produced during a slot. So we'll come back to that in a bit. So for the first few epochs, we have to pass in some randomness. Further randomness, though, is taken from the previous epochs. Based on, again, it is pseudo-random, so we're going to get a lot, but we're going to concatenate all of the different VRF outputs, the verifiable random function outputs, together. So this should be so difficult to compute that we can't actually use this to try to do any sort of attack based on knowing which validator is going to be producing a block next. Otherwise, you could DDoS that particular validator to try to knock them offline, and perhaps keep doing that to all of the different validators. So there are a couple of keys in Babe. So we call them session keys. Basic public key cryptography here, private key and a public key. But we're going to use these keys for some different things. The first is our block signing key. So this is just a way for us to provide a cryptographic signature that, all right, we validate this block. We're going to produce and validate this block, and you know it comes from me because I have signed it with my private key. You can verify with my public key that it's been generated and produced by me. Sort of the interesting thing, I think, the twist to this is the lottery key, which is it's our function for our verifiable, is our input for our verifiable random function. Where we have a secret key that's going to allow us to roll the dice, But we're also going to have this public key that proves to everyone else that we, in fact, did roll the dice reliably. We didn't cheat. We can actually produce a proof for that. And we're going to let everyone know ahead of time when we join the validator set, here is our public key. You can always prove that I didn't cheat, even if you can't see behind my scenes and behind the scenes, see my secret key and roll for me or roll ahead of me, but you'll know that I actually did it reliably and it's provably true. So a verifiable random function has a few parts. It allows us to generate some output using our secret key, then create a proof, again, using our secret key. X is our input, our randomness input, our seed that's from previous epochs, okay? And create a proof that others, I'm sorry, it's not displaying correctly, that last one here. We can actually get have other people look at the proof. They know our public key, so with the public key and the proof, they can tell that we did, in fact, roll randomly. We're not just cheating and taking up a slot whenever we want to. So here is just, if you're interested, how we get the entropy. Again, it's from 2 epochs back. And again, this helps us prevent some sort of attacks where people would be able to modify the randomness just by if we did just in the preceding epoch. At this point, this would be several hours back in time, and we're going to be prepared for it up here. So again, we roll our hidden dice, our verifiable random function. We get some value v, and if it's less than our target tau here, we're going to produce a block in this slot. As well as a proof for everyone else to know that, hey, when I signed up as a validator, I told you this was my public key. I'm going to use my secret key to produce a proof that I'm, in fact, rolling this, and you can check with my public key that I am following the rules. If the value that we produce from the VRF is above the target, though, we're going to collect blocks from other people. So we're going to check, hey, has anyone produced a block for this slot? If so, grab it, right? So we're just going to send it around to all the validators, communicate with all the other validators, send out this block and propagate it around the validator set. So at this point, we have a very simple best chain selection. So again, I already talked about grandpa from a really high level. Let's ignore all of that for now. For babe, just running by itself, which is perfectly possible to do, we have a simple best chain selection, which is the longest chain rule with ties broken by the first block that was received. So we have here a few different examples from the Genesis block G. We can see we have not the longest chain. We have one block, one chain that's just as long, but received the last block. Our particular validator received that last block second. And then we have the actual best chain, which is the longest, and we received that last block first. So once we know the best chain, again, we get the randomness from the epoch 2 before us, and by getting all of the VRF values from that, concatenating them together, and creating some new value that's going to act as a seed for our new input. So again, everyone should be agreeing by the time we have an epoch. These epochs are pretty long, and so everyone should be agreeing on what the epoch was to previous by the time we get to this point. Otherwise, you would have situations where you would continue to fork because people are using different concepts of epoch for their randomness. So people would disagree and think that others are not producing the right values, and thus we would see a fork. So this is basic Babe, but as we were producing this, we wanted to have a more constant block time. So here, we may have really long stretches because this is, Babe is probabilistic. So we may see periods where there are no blocks. You see this if you look at Bitcoin block distribution. Sometimes the mean time is 10 minutes, but that doesn't mean that you get a block every 10 minutes, right? Sometimes it's 55 minutes, sometimes it's 2 minutes. So we wanted to do something about that to make block time more constant. So when we say 6 seconds, we actually mean 6 seconds. So we added this concept of secondary blocks. So validators will basically take turns, like a sort of almost like a round robin, to produce these secondary blocks. So they're going to produce that function, so they're going to get the hash, the Blake2 hash of the epoch randomness, that value we already passed in, plus they're concatenated rather with their slot number, modulo the number of authorities or validators. So every validator should have a chance to make a secondary block eventually. But every slot will have either a primary block and a secondary block, or just a secondary block. But these secondary blocks, as their name implies, are secondary. They're outweighed by the primary blocks. So now we have this constant block time production. So the dark validators, they produce the primary block, and the light validators produce the secondary block. So we're always going to have some block being produced. But once we've added this, we need to make our best chain selection rule a little bit more complex. So now it's the longest chain as measured by the number of primaries. So we can see here, now our center one is not the longest chain. It has two primaries. We have two chains that are the same length, but one has more primaries, and so that becomes the actual longest chain. So we do have to modify our chain selection rule a little bit. So again, all of this is just for block production. Remember, so we've got our baby crawling along, producing blocks. Now, Grandpa is going to follow behind and start finalizing. So what allows us to do this, what allows Grandpa to work, we know the size of the validator set. Remember I said that was important. We needed to know that we're going to have n validators. And it turns out that they also have roughly equal stake. So I'm not going to cover that here. If you're interested, we got the fragment algorithm on the Polkadot wiki. You can, I wrote a nice explainer of that. But basically, whenever people are deciding on what validators to use, what to nominate, as we say, to put their stake behind, we end up equalizing it out. And those validators are going to get equal rewards, no matter how much stake is behind them. So if I have one validator with 9 million dots behind it and another validator with 3 dots behind it, they actually are going to have the same weight and get the same rewards. So now that we know that all these validators are going to be treated equally, they each count as one validator, none count as more than the other. If we can get a supermajority of validators to sign off, then we can say that, all right, this block is now finalized. It is not going to change. Okay? Now, remember I said that in a Byzantine environment, such as we're facing, we could face stalling because of this, right? If you think of like a classical, like a PBFT or a Tendermint algorithm or something like that, every time we produce a block, we're going to need to get 2/3 validators sign off on that, on what is the canonical block. But if there's some sort of partition or malice, then we're never going to progress beyond that absent some sort of intervention. So, but we know, again, that we're going to want to produce blocks even if there is some sort of stalling situation. We want to remain live. So Grandpa is this our finality gadget. It's going to allow everyone to agree on a chain. It's going to follow a very simple fork choice rule. And we actually, although we're using it with Babe, it really can work with any block production mechanism. any probabilistic block production mechanism. But our goal here was to be able to agree on many blocks at once. We knew that a one-by-one finality situation just did not meet our goals. And we may have situations where it takes quite a while for us to determine what is the canonical data coming in from the parachains, in which case finality will be stalled. We can't finalize if we're still arguing over what's happening on some other blockchain. And so once that does happen, we don't want to say, all right, well, we're now 6 hours behind. Let's go through block 1, block 2, block 3, block 4. That could take a long time. It could take to get back up to where we actually are. What we want, ideally, is to be able to jump forward as much as possible and finalize all one long chain to get us back to the point where we're producing blocks. And once again, have finalization be somewhat close to the block production rate. So, as I mentioned, with hybrid consensus, even though we have a bunch of validators that go offline or are not producing valid blocks or are equivocating, they're producing multiple sign-offs on what the valid block is, we can still continue producing blocks with Babe. So we're producing. Now, there may be some disagreement between the validators at this point on what is the right chain to follow, although with our longest chain, modified longest chain rule, we should see this converge relatively quickly. But we do know there will be some divergence, and possible, a couple of block chain splits. But as soon as Grandpa comes back online, as soon as we do have enough validators that are acting correctly, we actually can jump ahead, right, and finalize that whole chain at once. So how we do this, part of it is just standard, just 2/3 voting. So we use Ghost, greediest, heaviest observed subtree, which in a nutshell, we use to calculate this, it boils down to starting at the genesis block, keep including the child of the block that more than 2/3 of the voters voted for descendants of. So we know what percentage people have voted for these different blocks. And we can see that, well, 100% voted for this, 100% voted for this block, but once we get down here, we haven't reached that once we get to the third block, or second, depending on if you count it 0 or not, the 0, 1, 2th block, we don't have 2/3% on any of them. So Grandpa can't go forward, so it only goes down to that 0, 1th block. The head of that chain is going to be the finalized block. So digging a little bit more deeply into how it does this, every slot, we're going to have one validator selected to be the primary. This means something slightly different than the primary in Babe. And they're going to broadcast what they think the head is. They're just going to start the round, basically. Then all the validators, that's their pre-vote. They're going to then each apply the 2/3 ghost rule that I just explained to what they think should be their view of the chain. They're then going to pre-commit and broadcast that to everybody. And there's a second iteration where everybody gathers the pre-commits and determines, do we have a 2/3 agreement on this? But these votes are not on an individual block. They could be something further along. So we may have, what I mean by that is there may be different heights. So here, for instance, we have all these different possible forks to follow for what the canonical chain is. But an interesting thing that you'll notice here is that no conflicting chains have a common descendant. So, for instance, if I'm at 22 and 18 conflict, right? If I'm following 22, there's no way I'm going to get to 18, 16, 15, 14, or 3. Or if I'm at 19, well, 17, 13, 12, 11 are included in what I'm going to talk about. There's no way 10, 9, 8 or 18, 16, 15, 14 will be included. So by voting just at these different levels of blocks, then I can actually figure out, once I get a 2/3 percentage on a specific block, I also know that everything behind it should also have this at least 2/3 associated with it. So what this allows us to do is when we do drop out from finalization for quite a while, then we can very rapidly come back up to speed because we're going to finalize this whole chain instead of thinking, okay, so I'm going to have to check, is it 11, 8, 14, or 5? Is it 12, 9, 15, or 6? Is it 13, 10, 16, or 7? Rather, I can just finalize all at once. So this lets us, even in situations where there's a long period where finalization stalls for good expected reasons, like we have a bunch of disagreements between parachains or bridges on what the actual canonical chain is from them, or because of an attack, once we've gotten the bad validators off, we can very rapidly finalize and come back up to speed. So now we have our final best chain selection rule. So it's the longest chain as measured by primaries, so that's the babe part of it, on the last finalized grandpa block. So if we have our red block here as the last finalized block, we can see our top, yeah, I apologize, some of my numbers aren't showing up correctly. If we just imagine a bunch of 2s up there on that top chain. We can see here that is on the last finalized block, but it doesn't have the most primaries, even though it's the longest. For the second from the bottom, it's on the last finalized block, but it also doesn't have the most primaries. The most primaries on that bottom chain, but it's not built on the last finalized block. Remember I said grandpa's finalization takes precedence over babe's primaries versus secondaries. So that middle chain that's going straight turns out to be the canonical chain. Even though at first glance it looks short, it has the most primaries and it's built on the last finalized grandpa block. So, of course, people can always try to cheat. I already mentioned why they can't cheat in terms of generating a block, because everyone else can prove very easily that they're not producing the right verifiable random number function results. However, someone could do more insidious things, like drop off the network, like a griefing attack. They could just have all their validators drop off. So we do have proof of stake protection against that in the form of slashing. So you're basically off-chain, all the validators that are part of the active validator set are storing what you have done. And if you do something malicious or even perhaps not that malicious, like drop off the network, something that would be detrimental to the network, you have the possibility of being slashed. One of the interesting things I think about this is that the slashing penalties increase as the number of participants increase. If one validator drops off the network, well, stuff happens. There may have been a lightning strike and their node got destroyed. There could just be really bad latency. They're hopping over 3 satellites because they have a node in the middle of the Sahara or something. So if there are a very few number of validators that go offline, well, that's fine. We're not going to slash just because of that. However, as more validators go offline, this is a higher possibility that something is actually wrong, that either this is an attack on the network or we have some incompetent, that's probably too strong of a word, I apologize, validator runners who they put all their validators on the same Amazon instance or something. So the slashing penalties increase as the number of participants in one of these Byzantine failures increases. There are 3 different ways right now that someone can be slashed. One is by not participating in the network, so not issuing blocks when they should. and not responding to I'm online pings. So you always, even if you don't produce a block, you need to at least tell the other validators, hey, I'm online, I just, my VRF never actually produced something. And because we're storing all of this information, the validators offline, no matter what chain ends up being finalized, then we're avoiding the nothing at stake problem, because no matter what happens, we can get their bonded stake and slash them going forward. All right. So just in conclusion, we have two different protocols. Block production is done via Babe. Finalization is done via Grandpa. They're entirely separate mechanisms. They allow provable finality, but we don't have the drawbacks of stalling. We basically fall back to probabilistic finality using Babe in case there is some sort of major issue. It is used in Polkadot. The mainnet is coming soon, but we have been running an early unaudited release since August of 2019 called Kusama. And again, we've called it our R&D network for risky and dangerous because we knew it was an early release, there were going to be problems, and we've actually seen some instances where we had finalization failures and we had finalization stall out, and yet we went for tens of thousands of blocks with just Babe acting as our probabilistic finality fallback. So again, I'm not saying that we're breaking any like cap theorem rules or anything here, but it does provide a really empirically tested and valuable way of having liveness, but also that provable finality that we can use for our main goals of producing a blockchain that can interact with other blockchains very easily and share security amongst all of these blockchains. So if you're interested in going more into depth on the research of Babe and Grandpa and some of the other things that we're working on, if you go to research.web3.foundation, there are quite a few papers and interesting articles there. If you would like to get in touch with me, I'm on Twitter at Bill Laboon, or email bill@web3.foundation. So, thank you.
Thanks very much, Bill. So we have some time for questions. So again, please feel free to come to the microphones at the edge. I'll kick off with a softball question, Bill. So I know there's quite a lot of activity going on with getting towards deploying for production and mainnet and so on. So do you want to give us the absolute latest on the ground with the progress that you're making?
So there's a lot happening, fixing security audit issues that we found. Getting some of the work on Substrate, which is how people produce parachains. So it's basically like a Ruby on Rails for blockchain, I like to describe it. So our system that lets others create these parachains for themselves. Cumulus, which is our way of interacting with the network, finishing up our availability and validity, as we call it, like making sure that as these parachains communicate to the relay chain, what their state transition was, what their blocks are, how do we get that to all the validators in a good and efficient way. So those are some of the final things that we're working on before mainnet's launched.
When mainnet?
Soon. TM.
Soon TM, 2 weeks TM.
Yeah.
First question over here.
Yeah.
Thanks. I guess I have two quick questions. Briefly, could you say a little bit about how randomness is provided for the first couple of epochs? I just thought that was interesting. And then the other one was, what happens when you finalize a block and it has a ultimately incorrect representation of the state of a parachain?
Yeah. So good question. Well, two good questions. So the first question, sorry, say that. I should have just answered that at first.
Randomness.
Right. So the first two epochs of randomness are injected into the system. Like they're part of the chain specification of what the first two.
They can't be used to attack the way that it's supposed to protect in subsequent epochs.
Right. So you would think that because all right, well, we could set this. However, when we launched the network, it's proof of authority at first, and so we have a set of Web3 validators that are going to be running the network, but you're right, otherwise that would be an attack mechanism. By the time that we will transition to a traditional proof of stake network, then we'll be, I mean, I don't know exactly how many blocks, but last time we were something like 100,000 blocks before we transitioned over to proof of stake. So that pseudo randomness has had time to build, or that randomness has had time to build.
The finalizing a block that has an incorrect representation of a parachain state.
Right. So parachains we wait until they have are giving like their final representation. Obviously, in some networks, this is going to take much longer than others. So something like Bitcoin, we're not going to be like reading directly off the network. So what I mean by that is, we can have these external blockchains be virtualized as parachains. So in the event of some sort of reversion of finalization, so basically we're waiting a long time for those before we wait for it. So we really shouldn't see that in practice. If we do see that, it's going to point to a major slashing event because it means that these parachains have been lying to us. And since there's going to be bonds for that, they're going to lose a lot of value. We don't expect this to really happen in practice.
Sorry.
Yeah. No.
The bonds cover like a potential double spend on Bitcoin or something?
Yeah.
Bill, if you could repeat the question for the viewers
Oh,
at
I'm
home.
sorry. Yeah. Yeah. So to have a parachain connected to the network, there's a large bond of it's an auction base, but it's going to be we're expecting in the 50,000 dots or something like that, which would be a very large amount of actual economic value behind them, and that if you are a blockchain or a parachain that's sending invalid data, you could be kicked off from this, which we as part of these bridges right now, there is like an economic bond associated with those as well.
All right, next question over here.
Yeah, I have two questions as well. The first is for the sort of the blocks where no VRF won the lottery, you're using the concatenation of the VRF outputs from a previous epoch,
Yes.
to determine the randomness. Doesn't that allow malleability in the random output through participants electing to fail to produce their VRF output? And then the second question
Wait,
is...
so just because I obviously can't remember more than one question at a time,
Sure.
I'm just going to go with that first. Yeah. So yeah, I mean, there is possible malleability, but because we're taking the hash, you would really need to have all of the validators in on it. And since they also will not be able to predict what those validators ahead of time, since they're using their own VRFs with their own secret keys, people aren't going to be able to predict really what the block production, what those VRF outputs are going to be ahead of time.
But the last person to put a VRF in has the choice to elect to do that or not, right?
Yeah. So yeah, if you're yes. So theoretically, you could, but I guess my point is that like that concatenation, of even subtracting that out, getting that hash value for later, since you're not going to be able, you can't tell ahead of time what those VRFs are going to produce unless you have the secret key.
Oh, it's commit and reveal. It's not. You're talking about hashes there. So
you'll know the input, like the randomness input of that epoch.
Right.
But when it gets pushed into the VRF, you don't know what the output of that VRF is going to be unless you have the secret key as well. So even if you have the input or are able to modify it, you're not going to know how that impacts the values that are coming out of the validators' VRFs. Because each of the validators is going to have their own VRF that has a secret key associated with it.
Right, but didn't you say that you're taking all of the VRF outputs from an epoch and concatenating those?
Yes, and acting that as the input for the VRFs going forward.
Okay. Well, my second question was, you're taking the modulus of that VRF output by the length of the list of authorities. Does that mean that this is a permissioned blockchain in the sense that?
No, so he asked, if you're taking the modulo of the authorities, then isn't it a permission blockchain because you're saying what the authorities are?
Yeah.
So that's only, so two things. I think that for the primary block production where we're using VRFs, we're not using that algorithm for the secondary block production, which uses the modulo authorities length. So that's a separate algorithm just for producing secondaries, which doesn't involve the VRFs at all. So that's like the round robin, the secondaries, which, as we know, that's going to be less secure because that's deterministic. It doesn't. That would be vulnerable to malleability attacks. We know all the input into it.
That was the part I was talking about.
Oh, okay. Yeah, I misunderstood. Yeah, so that's a separate. That's like our backup, which we understand is not as secure, and so it is always outweighed by these primary blocks that are being produced. So only the primary blocks are produced with VRFs. So the second, understanding that the modulo authorities length, that is the number of validators, which is the top end stakeholders, but those stakeholders are not by themselves authorities. I mean, so authorities is probably the wrong word to use for that variable. By authorities, I just mean the number of validators in the active validator set, which are the top N stakeholders in the validator set.
Okay, thanks.
So perhaps it's kind of a semantic thing, and I think that will come back to some of the themes we talk about in this conference. We're so early in this thing that we use different words to mean the same thing, or the same words to mean different things.
Yeah, I mean, that's something, I mean, with hybrid consensus, right? Like how Decred uses hybrid consensus is different than how we use the term hybrid consensus.
I'm not going to even ask you for your definition of a blockchain.
Yes.
So we're going to wrap up there. Thank you very much, Bill.
All right, thank you.
Yeah.